Welcome to this next lecture on acoustics. In the last class we derived the interior Neumann green function. Today we will do the interior Dirichlet green function. If this is my kh integral over a surface, then G del phi dot n minus a phi del G dot n ds of r. In this case we are trying to look for a green function g, which is, let us say, this small g plus another g h, and we will call it g d, that is 0 on S. Okay. So then we replace the free space green function with Gd here and del Gd dot n here, and because Gd is 0 on the surface, this first term goes to 0, and so we are left with the second term over here. Okay. So phi dash or phi of r dash is equal to integral over S minus phi of r del Gd dot n. Okay. So now let us look at this. So the logic is the same. We have to have a GH which satisfies the del square plus k square GH equal to 0, del square plus k square GH. In here del square operates on r dash, theta dash, phi dash, and such that G plus GH is equal to 0 on S. Okay. So now we have the expansion for G, right? G r slash r dash, we have the expansion which is given by minus I k summation n equal to 0 to infinity j n of k r dash h n of k r summation m from minus n to n y m conjugate n theta dash phi dash y m n theta comma phi. So because the green function is between 2 points r and r dash, r, okay, the r refers to r comma theta comma phi, and r dash refers to r dash comma theta dash comma phi dash. So now what we have to do is find a GH. We have to find a GH. Okay, and it's done intuitively. Okay, so we have an IK. Okay, and we have to sum from n equal to 0 to infinity, and this evaluation will take place on r equal to a, so I have j n of k r dash h n of k a by j n of k a j n of k r summation m going from minus n to n y m star n y m n. I am not putting the arguments again and again. Okay. Now this has theta comma phi, this has theta phi, and this has r, and you can see that this is indeed the solution to the homogeneous Helmholtz equation, and we saw that using the method of separation of variables. Okay. Now you can see that when r is equal to a, this becomes a. When r is equal to a here, these two terms will cancel, this and that will cancel, and this will exactly be equal that with a negative sign, so that this equation is satisfied. Okay. So now what we have here is an interior problem. Okay. So now here what happens, the n points in that direction, and of course the r also points in that direction. Okay. So what we have to find now is del g del n. Okay. So del g d over del n r slash r dash at r equal to a, how does it look like? Okay, is the derivative of this plus the derivative of this. Okay, so how does it look like? I have minus I k square summation n going from 0 to infinity. Okay, j n of k r dash and derivative of this with respect to r evaluated at a, so h n dash of k a minus the derivative of r applies only here. Okay, minus j n of k r dash Hankel k a by j n of k a and j n dash of k a plus the two y's. Okay. So now if we try to find a common term, minus I k square summation n from 0 to infinity, I will pull out the j n k r dash outside, which is common. Then I have Hankel n dash of k a minus Hankel n of k a by j n of k a into j n dash of k a and this y sum. Let me keep it a little away, into y conjugate y, y conjugate y. Okay, and the Hankel function is Hankel function of the second kind. Okay, so which is equal to j of n minus I y of n. So now what we have is that if we use this Hankel function definition, we have inside Jn kr dash and multiplied by Jn dash minus Iyn dash. The Ka I am avoiding right now, minus Jn minus Iyn, arguments are Ka, then Jn, okay, into Jn dash, and this gives me I Jn kr dash minus Yn dash plus Yn by Jn dash, okay, and we know, by now we know that minus Jn dash of x Yn of x plus y dash n of x Jn of x gives me 1 over x square. Okay, so I have this opposite of it, I have minus Jn Yn dash, okay, minus Jn Yn dash. So this is minus 1 over x square, x is Ka. So what I have is that equal to minus I k square sum over Jn of kr dash Jn of kr dash into minus 1 by k square a square into 1 by Jn of Ka summation y star y. Okay, so let us see del Gd by del n r dash evaluated at r equal to a looks like there is an I over here which I missed, so there is an I over here, so this becomes I square. Okay, so I have I square into minus 1 is 1, then I have a minus and then k square goes, so I have minus 1 over a squared summation n going from 0 to infinity Jn of kr dash by Jn of Ka, then summation m equal to minus n to n y m star n theta dash phi dash y m n theta comma phi. Okay, so this is my, so my now my integral will be phi r dash is equal to minus, and this minus goes with that minus, so I will remove that, integral over the surface area del Gd, no, that would not be right, let me just minus 1 over a square, sorry, 1 over a square sum over n 0 to infinity Jn kr dash Jn of Ka summation m y m conjugate n theta dash phi dash y m n theta phi into phi. okay, A and ds0, okay, and this ds0 will have the angular functions, okay, a square sine theta d theta d phi, okay. So that's the Dirichlet interior green function, okay. So next what we will look is the exterior functions, okay. So we will look at the exterior Neumann green function. The logic is the same. Now we are interested in the exterior region here, so that n points in this direction, but r points in that direction, okay. So del n is opposed to del r, that is important, okay. And my phi of r dash is integral over an area which is g r dash del of phi dot n minus phi del g dot n ds of r, okay. Now here again what we are going to say is that we are going to bring in a new function, Neumann green function, which is g plus a gh, okay, but such that del gn by del n on r equal to a, which is equal to now minus del gn by del r on r equal to a is equal to 0, which means minus del by del r of g plus gh equal to 0, or del g by del r is equal to minus del gh by del r, okay. Now for the exterior, this green free space green function g, okay, r comma r dash, which is e to the power of minus I k r minus r dash by 4 pi magnitude r minus r dash, has an expansion. That expansion is given by minus I k summation n equal to 0 to infinity j n of k r Hankel function of k r dash summation m equal to minus n to n y m conjugate n theta dash phi dash y m n theta comma phi. Okay. In this case, r has to be less, r is the integral coordinate, it has to be less than r dash, okay, and this is the Hankel function of the second kind, okay. So now if we have to find a corresponding homogeneous function. What do we have? We have to find the derivative of this with respect to r. Okay, so that is going to be first del g r dash of r is equal to minus I k square summation n equal to 0 to infinity j dash of n k r Hankel function second kind k r dash, then summation m from minus n to n y conjugate y. Okay, and this is evaluated at r equal to a. Okay, so this becomes a. Okay, now what we have is del g by del r must be equal to minus del by del r of g h. Okay, r dash at r equal to a, where g h is the solution to the homogeneous equation. Okay, so let us see what form it takes. We have g h r. This is kind of in an intuitive manner we are doing it. Okay, so there must be functions which satisfy the homogeneous equation and it should cancel this term. Okay, so g h, let us say it has to have an I k, so that an r derivative brings one more k. Okay, n equal to 0 to infinity. Then I have a Hankel function k r dash which is there on the top also. Okay, then here j n dash of k a by Hankel n dash of k a and Hankel function of k r, because it is in the exterior domain, r can go up to infinity. It is a Hankel function. Then of course this which here does not play a role because we are at the center of a sphere and evaluating on a spherical surface. Okay, so if I do the del h by del r, you can see r equal to a. If I do that, you can see that here is where the r is, so I get an I k square. Then I have this sum, of course, and Hankel function nothing changes, which is there here also. Okay, and then I have j n dash k a, which is a constant, does not matter, h n dash k a constant. Then here we took a derivative, so this will become h n 2 dash evaluated at k a, and this m sum this cancels with this. I have j n k a h n dash h n k r dash, sorry, this should be, okay, dash is there, j n dash. Okay, so now I have j n dash here, j n dash here, k a h n k r dash, j n dash here at k h n k r dash with a minus sign. Okay, so they will cancel out. Okay. So now what is the net Neumann green function? Neumann green function is g plus gh. My n and h are looking similar, that is the problem. Okay. So that my phi of r dash is going to be the integral over the spherical surface, okay, gn r dash. It is evaluated at r equal to a, evaluated at r equal to a, and ds at r equal to a square sin theta d theta d phi, okay, d phi. Okay. Now how does gn look like? The gn now looks like what? r dash, it looks like minus ik, okay, and it has to be evaluated at r equal to a, okay, minus ik summation n going from 0 to infinity jn of kr Hankel function second kind kr dash minus Hankel function kr dash jn dash ka by Hankel n dash ka Hankel n kr and the summation, and these are all second kind, they are all second kind. So this is equal to minus ik sum over n then I take out the common Hankel function n, this is my n, to kr dash, and I have jn of ka r evaluated at a minus j dash n ka by Hankel n dash of ka Hankel n of ka all second kind, okay, second kind summation over m, okay. This Hankel function of second kind is just jn minus I by n, okay. So that this entity, I will not repeat, this entity becomes equal to Hankel function kr dash by Hankel function dash ka into minus of I by k square a square. Okay. So if we now substitute it above, okay, so I get this I and that I, they give me a minus 1, so I get a minus 1, then the k cancels, I get a k a square, I get a sum over n h n second kind k r dash h n dash k a, then the sum over m minus n to n y m conjugate n theta dash phi dash y m n theta comma phi, and this is the Neumann green function r r dash evaluated at r equal to a, and it goes in here. Okay, so that's the exterior Neumann green function. Okay. Similarly, the last one, similarly, without a lot of effort, okay, the exterior Dirichlet green function. Okay, so I have my G, which is given by minus I k summation n going from 0 to infinity. J n will be in a kr form, h n will be in kr dash form, summation over m y conjugate y on a sphere. We are on a sphere. Okay, we are centered at the center of the sphere and we are looking at the exterior region. So n is this way and r is that way. Now I choose my gh, okay, so that I have ik, they have to sum to 0, okay, n equal to 0 to infinity. Then I have j n of k a, Hankel function of k r dash by Hankel function of k a and Hankel function of k r, and this summation h n, this is h and this is n, this is h, this is n. So now you can see that if I substitute r equal to a over here, this goes away and I am left with j n k a. Here I evaluated r at a, I have j n k a. Here I have h n k r dash, here I have h n k r dash. I have a negative here, I have a positive here, they will sum to 0. Okay, and because this is h n of k r along with y m n of theta comma phi, the spherical harmonic, gh is a solution to the homogeneous wave equation for the domain that extends to infinity. Del square plus k square gh, in here del square operates on r dash theta dash phi dash. Okay, so now if I have phi at r dash is equal to integral over a spherical surface g d, okay, del phi dot n minus phi del g d dot n ds on a sphere, then this goes to 0 and I am left with this term over here. Okay, so how does del G d del R look like? Del G d by del R slash R dash evaluated at R equal to A, okay, look like. So it looks like, let's see, we have derivatives from here and here. So I have minus I k square, okay, then I have the sum n, then I have j n dash k a, j dash n of k a into h n k r dash, h n k r dash, okay. Then this next g h term comes in with a derivative, that is minus j n of k a, h n of k r dash by h n of k a into h n dash of k a, and this sum over m, okay. So now if we look at this, I have minus I k square summation over n Hankel function k r dash and j n dash k a, I am going to let go for now, minus Hankel n dash by Hankel n j n, okay. So by now you should know that j, let us do j n dash, right, okay. So I have Hankel n inside Hankel n k r dash and inside j n dash minus j n dash minus I y n dash by j n all at k a minus I y n into j n, okay. So that results in I h n k r dash, this I will keep as h n k a, h n of k a, then I have minus j dash n y n plus y dash n j n, okay. So this is 1 by x square. So in this case this is just 1 by k square a square, okay. So what I have now is equal to minus I k square summation Hankel function of the second kind k r dash, and this interior thing gives me an h n of k a, and this gives me an I, I have an extra I, and 1 over k square a square, okay, and this sum over m. So this I goes with this I and minus, and then this k square goes with that k square. So I am left with del g d by del let me see, we did del g del r, right. So del g d del r, is equal to 1 over a square summation n goes from 0 to infinity h n to k r dash by h n to k a, and this sum over m y m star n theta dash phi dash y m n theta comma phi. Okay, and how does it sit in there? We have minus del g del n, right, in the kth integral. So del g del n is minus del g del r. So I have phi of r dash is given by integral over the spherical surface del g d over del r into phi of r and ds which is a square sine theta d theta d phi. Okay, so that is the exterior Dirichlet green function. So we have more or less covered the type of green functions we will use. We'll start looking at some problems next class. I will close the lecture here. Thank you.